I mentioned that one form of a system can be a nonlinear system. So the question is, how do we work with a linear system if we're given a nonlinear system? And this process then is called linearization, where we can get a linear approximation of a nonlinear system. And there are a couple methods of working with this type of system. There's a variational method and deviation variables method. In a sense, we're actually going to be using both methods, but these are the approaches we would take. So given a state model, z dot is equal to, so here is a linear time-varying system. The output equation, the output is also a function, in general, a nonlinear function of the state z and the input v. Generally speaking, when we linearize a system, we are concerned with some kind of operating condition. The most common operating condition to work with for a system is what's called an equilibrium condition. An equilibrium condition is a condition where the system can basically be at rest. So in general, there are some signals, z equilibrium and v equilibrium, such that z dot is equal to 0. So what does z dot equals 0 mean? That means z is not changing. So we can think of it as being at rest. The system is not going anywhere, it's not moving. So since we have this equation that describes z of t, that means if we were to plug this function of z in here and this function of v in here, we would get 0, identically 0. Okay, so this is the equilibrium condition. This describes an equilibrium condition, and we will usually use an equilibrium condition when we're linearizing a system. We can now define the deviation variables. X is equal to z minus the equilibrium z. U is equal to v minus the equilibrium v. And for the output, y is equal to r minus the equilibrium r. So this is the r that you get when we're operating at the equilibrium condition. So note that I can solve this equation for z and for v, and we can plug those back in here and get this. Okay, so what does this tell us? When z is equal to ze, that is when x is 0, and v is equal to ve, that is when u is 0, the system is in equilibrium. So what this does is that the deviation variables take us from the equilibrium condition ze, ve to the condition 0, 0. So basically centers the equilibrium condition at the origin. Now we take our function, which is a function of both z and v, and remember z in general is a function, is a vector, v in general is a vector, and we can write out a Taylor expansion for many different kinds of nonlinearities. So what I'm showing you now is a particular type of linearization. It uses the fact that our system may be smooth, that is, I can actually do a Taylor expansion. Okay, so if we can take a Taylor expansion of the nonlinear function, then this is what it looks like. And you can see it starts getting messy. Okay, so what's that happening? So I can evaluate this at the equilibrium condition, plus I take the partial derivative of f with respect to z. Remember, f is a function of z, so I can take the partial of f with respect to z, evaluate it at the equilibrium condition, multiplied by z minus ze. Okay, so this is the Taylor expansion. Then I have the second derivative with respect to time. Okay, second derivative of f with respect to z. And when I do this, this quantity becomes, instead of being, so here f is a vector function, instead of being a vector, this now becomes a matrix. When I take the partial derivative of f with respect to z, that becomes a matrix. When I take the second partial with respect to z, this actually becomes what's called a 3D matrix. Okay? And so it's definitely more complicated. So this is how that is expressed. So whenever you studied Taylor expansion, for example, in your calculus class, you didn't look at it when the variables were vectors. You looked at it when the variables were scalars, and that makes things a whole lot easier. Now, notice I have two variables, z and v. So what I did with z, I now do with v, partial derivative of f with respect to v, evaluated at the equilibrium, times v minus ve, and so forth. So I take all the partial derivatives with respect to z, all the partial derivatives with respect to v, and then I have the cross partials. So this is the second partial of f with respect to z and v, and so forth. And we can have, as you go for higher powers of the derivative, we can have all different kinds of combinations. I can have partial squared of z, partial v, partial z, partial v squared, and so forth. So this is what the Taylor expansion for this vector valued function of two vector variables. Okay, that's what it looks like. All right, so linearization is really obtaining a linear approximation of the nonlinear system. Okay, so here's our Taylor expansion. And notice that this first term here, f of ze and ve, since ze and ve are associated with an equilibrium, this term goes away. And now we're also going to reject all the higher power derivatives, second derivatives, third derivatives, and so on. So we're only left with the first derivatives. And so we can write f of z is approximately equal to this. Okay, so this is the approximation we make. So remember, when we take the partial of f with respect to z, we're getting a matrix. We evaluate at equilibrium, in which case this becomes a constant matrix, or maybe a function of time. Similarly with f with respect to v, this also becomes a matrix. So we're just obtaining a linear approximation of the nonlinear system. So x dot now, which is the derivative with respect to time of z minus ze, we will consider a constant equilibrium condition. Ze is a constant, and so we're taking the derivative just of z, which is z dot. But z dot is given by f of z and v, which is approximately equal to all this stuff. This quantity is what we've called x, this quantity is what we've called u, and now I define this to be a, and this to be b. And so we have x dot is equal to a x plus b times u. And that is a linear state model. So in linearization then, we would basically have x dot is equal to ax plus bu, y is equal to cx plus du, where a, b, c, d are given by the partials of f and g with respect to z and v. We'll take a look at this when we look at practice problems.